Hello, everyone, and I'm back. And this time we're going to do another lecture series. And on this video, we're going to talk about differential equations. And we know that differential equation is really an important tool in mathematical modeling and in simulating certain phenomena and understanding how they operate. And this model, with the aid of differential equation, can help us solve real life problems. And let's now understand the idea of differential equations. So before we formally define what a differential equation is, let's take a look on what a differential equations or DE actually is. So let's have here an example. Say we let y equals a function f of x, and then I have here y double prime plus 3y prime equals negative 2y, and this is actually an example of differential equation. So there is a presence of the second derivative of y, since y is written in terms of x, so we have here a second derivative of y with respect to x, and the first derivative of y with respect to x. And this differential equation can be written of the form f double prime of x plus 3 times f prime of x equals negative 2 times f of x. Or if we want to use the Leibniz notation, so we have the second derivative of y with respect to x plus 3 times the first derivative of y with respect to x is equal to negative 2y. And these three equations mean the same thing. And you know that the solution to this differential equation is really a function or set of functions. Now, if we could still recall that when we solve equation in algebra, the result are numbers or is or are numbers. So this time, when we are talking of differential equation, the solution is actually a function or the set of functions. Now, let's have some examples. Say if we let y of x equals e raised to negative 2x, so we might have to look for the second derivative and the first derivative. And you should recall some concepts of differential calculus, because actually we might be using the concept of or the theories of derivatives in most of the cases of differential equations. Okay, so since we have here a presence of y prime, so we first differentiate this by applying the derivative of an exponential function. So we can say that y prime of x is equal to e raised to negative 2x times the derivative of negative 2x with respect to x. And that will lead us to y prime of x equals negative 2 e raised to negative 2x. And then applying the same principle, differentiating the first derivative will give us the second derivative, and that is actually equal to positive 4 e raised to negative 2x. Now, we have here y double prime, y prime, so we can now create this differential equation with respect to x. So this y double prime plus 3y prime equals negative 2y can actually be written of the form. This is where your y double prime, which is actually equal to 4 e raised to negative 2x. You just place it here. And then plus 3, yeah. Then y prime is equal to negative 2 e raised to negative 2x. So you have here 3 times negative 2 e raised to negative 2x and equals negative 2, and y is represented by e to the negative 2x. So we have here 4 e raised to negative 2x plus 3 times negative 2 e raised to negative 2x equals negative 2 e raised to negative 2x. And then simplifying, you just multiply 3 and negative 2. So you shall have 4 e raised to negative 2x minus 6 e raised to negative 2x equals negative 2e raised to negative 2x. And then when you combine these two expression, you now have actually will become negative 2e raised to negative 2x, and in fact that is equal to negative 2e raised to negative 2x. So what does it mean? So this means that the function e raised to negative 2x is a solution. Yeah, it's a solution to this differential equation. And actually there are a lot of expression or equation that can be a solution to this differential equation. So that's why the solution of a differential equation might be a function or set of functions. Okay, so to formally define a differential equation, we have seen earlier that any equation which contains derivatives are called differential equations. And they can be classified either as ordinary differential equation or ODE or partial differential equation or PDE. Some examples of differential equations are as follows. We have dy dx equals sine of x. I have the second derivative of y with respect to x plus 4y equals 0. So here, there is the presence of the first derivative of y with respect to x, dy dx. And on the second example, we have the presence of the second derivative of y with respect to x. So since these two equation contains derivatives, then they are called differential equations. Another example, the quantity x squared plus y squared dx minus 2xy dy equals 0. We have seen here an operator dx and dy, which means a change of x or a change of y for dy. And obviously, there's a presence of differential or derivatives, then we say that this is a differential equation. Some more examples are as follows. So you have partial derivative of u with respect to t is equal to h squared times the quantity, the second partial derivative of u with respect to x, plus the second partial derivative of u with respect to y. So you have seen here a partial derivative. So we might say that this is a partial differential equation. And then equation 1, 2, and 3 are ordinary differential equations. So with this example, we can easily identify whether a differential equation is an ODE or PDE. If you have seen a partial derivative, yeah, in the equation, then that is a partial differential equation. And if you see, an ordinary derivative or total derivative, then you see the differential equation is really an ordinary differential equation. So it's easy to identify whether it is ODE or PDE. So just take a look on the symbol. When you see a symbol like this, yeah, it's ODE. When you see a symbol like this, so it's PDE. Some other examples of differential equations are as follows. So I have the second derivative of v with respect to x plus the second derivative of v with respect to y is equal to 0. And we also have here L times the second derivative of I with respect to t plus R times the first derivative of I with respect to t plus 1 over c times I equals E times omega cosine omega of t. Okay, some more. We have here the second derivative of w with respect to x to the third power minus xy times dw dx plus w equals 0. We have the third derivative of x with respect to y plus x times dx dy minus 4xy equals 0. So these are our examples of differential equations. Now, in the study of differential equations, so we have to consider the dependent and independent variable. And when a differential equation involves one or more derivatives with respect to a particular variable, yeah, that variable is called independent variable. And a variable is called dependent variable if a derivative of that variable occurs. Say, take a look on this example. We have here dy dx. So we have variables x and y. So based on the definition, we can say that y is the dependent variable. And since there is an occurrence of the derivative of a certain variable x, we say x is the independent variable. Now, when you take a look on the position of y and x on the operator, so it's easy to identify which one is dependent and which one is independent. So you can see that, yeah, taking the case of a fraction, yeah. So the variable here is called the dependent, and the variable under the symbol is the independent variable. So for from our example, equation number 6, you have L times the second derivative of I times with respect to t, sorry, plus R times the first derivative of I with respect to t plus 1 over c times I equals E times omega cosine of omega of t. Okay, so we have here, we can see here that I is our dependent variable. You can see it right here. Okay, and we can see that T is our independent variable. You see it right here. Okay, so what about L, R, C, E, omega? Okay, how are they called? They are called parameters. So L, R, C, E, and omega are called parameters. Another one. So we know that on this differential equation, the second derivative of v with respect to x plus the second derivative of v with respect to y equals 0, we see that v is our, yeah, you got it right, dependent variable, and x and y are independent variables. So we see here that there are two independent variables present on our differential equations. Okay, another one. All right. So take a look at equation number 3. So you have quantity x squared plus y squared dx minus 2xy dy equals 0. So which one is dependent and which one is independent variable? Now, if we manipulate this equation, we can have here an equation like this. So we have x squared plus y squared. You can just simply put dx here, dx, or the other way around, say you put dy here or dy, so we can have here the quantity x squared plus y squared dx dy minus 2xy equals 0, or the other way around, so you have x squared plus y squared minus 2xy times dy dx equals 0. So from here, and equation number 1, we can see that x is the dependent variable and y is the independent variable. On the second equation, we see that y is the dependent variable and x is the independent variable. Okay, so we have x dependent and y independent for the first equation, and we have y the dependent variable and x the independent variable. Okay, so another characteristics or attributes of the differential equations are its order and degree. Okay, let's talk about the order of the differential equation. So you know that the order of a differential equation is the highest order derivative appearing in the equation, whereas the degree, yeah, is the power to which the highest order derivative is raised. Okay, remember that the order is the order of the highest order derivative appearing in the equation, whether it is second, third, fourth derivative, fifth derivative, and degree is the power to which the highest order derivative is raised. Okay. Let's try to examine this differential equation. So you have here the presence of the second derivative of y with respect to x and dy dx, that's the first derivative. So again, this is the second derivative and this one is the first derivative. So clearly, we can say that the order of this differential equation is equal to 2 since the order of the highest derivative is 2 second order, and you know that the second derivative of y with respect to x is raised to the first power, and that the first derivative of y with respect to x is raised to the third power, although the power 3 here or the exponent 3 here is larger than 1, but based on our definition, yeah, the degree is the power to which the highest order derivative is raised. We say that the degree is equal to 1, not 3. Okay, another one. In general, yeah, in general, if we have a function, a DE, yeah, if we have a differential equation of the form f of xy, y prime, y double prime, y triple prime running until the n minus 1 derivative of y, until nth derivative of y equal to 0, and this is an ordinary differential equation of nth order. So that's nth order ODE. Okay, let's have some example, right? So you have the quantity d squared w over dx squared cube minus xy dw dx plus w equals 0. So what did you see? Yeah, you get it right. You have a second derivative of w with respect to x and the first derivative of w with respect to x. So the order is equal to, yeah, you got it right. That's 2. And the degree, so you take a look. You take a look on the highest order, that's 2. And to what power it is raised, that's 3. So therefore, the degree is equal to 3. Okay, so it's a third degree differential equation of order 2. Another one, say y double prime squared minus 3y prime cubed plus y equals 0. Again, there is the presence of y double prime and y prime. So we say that the order of this differential equation is 2. It's second order and second degree differential equation, ordinary differential equation. Okay, another one. So you have here cosine of the third derivative of y with respect to t plus the first derivative of y with respect to x to the second power is equal to x. Okay. So when you try to determine the order of this differential equation, so you take a look on the highest order appearing on the equation. So you see here the third derivative and the second derivative, or the first derivative rather, sorry. Okay, so what is the order of this differential equation? Let me see. Okay, and that is of order 1. Why is it order 1? Sir, you have here the third derivative of y with respect to t, and this is just the first derivative of y with respect to x. And when you try to look at it, the third derivative of y with respect to t can be found as a parameter of cosine, and that cannot be used as order of a differential equation. So that's why we have to consider dy dx as the highest order of this differential equation. So that's why the order is equal to 1. One more, you cannot use 3 as the order of this differential equation since the third derivative of y with respect to t appears as a parameter of our cosine function, of our transcendental function here. So we have to consider dy dx as the highest order derivative. And since it is raised to the second power, we say that the degree of this differential equation is equal to 2. So this is second degree differential equation of order 1. Okay, another one. So we have the square root of dy dx to the second power minus 2y equals the second derivative of y with respect to x. And you can see, right, that there is a presence of the radical, in this case, that's square root. Okay, so what are we going to do? Before you identify the order and the degree of this differential equation, you have to manipulate the given equation. So how do you do that? So you just take a square of both sides, leading you with, okay, so this will become the derivative of y with respect to x to the second power minus 2y is equal to the second derivative of y with respect to x to the second power. So the resulting differential equation can now be characterized based on its order or degree. Okay, when you try to look at the resulting differential equation, there is the presence of, again, dy dx and d squared y dx squared, or the first derivative and the second derivative. So what is the order of this differential equation? You get it right. So that's 2. It's a second order. And the degree, so to what power the second order derivative is raised, and that is equal to 2. So this is a second degree differential equation. Another one, let me see. Okay, so you have 1/2 y squared times the quantity y prime to the third power plus 3y double prime equals sine x squared. So again, there is the presence of y prime, y double prime. So clearly, we can conclude that the order of this differential equation is 2, and yeah, the degree is equal to 1. Again, although the highest power of our derivative is 3, but as we refer to our definition, the degree is the highest power to which the highest order derivative is raised. So therefore, the degree of this differential equation is equal to 1. Okay, so differential equations can be classified either as linear or nonlinear. Okay, so how do we define a linear differential equation? Okay, if each term of the equation which contains a variable of the set or any of their derivatives is of the first degree in those variables and their derivatives, we say that it's linear differential equation. And if it is not linear, then we say it's nonlinear differential equation. And the general form of a linear differential equation is given by b sub 0 of x times the nth derivative of y with respect to x plus b sub 1 of x times the nth minus 1 derivative of y with respect to x, running until b sub n minus 1 of x times the first derivative of y with respect to x plus b sub n of x times y equals 0. So you just take a look on the position of our variables. So our dependent variable is y and the independent variable is x. So you have to take into consideration, okay, the expression that goes along with our derivatives. It should be expressed in terms of the independent variable. So this is x, so this must be, this is x, so this must be expressed in terms of x. Now, sir, what will happen if there is the presence of y here? So if that happens, then we cannot say that it's linear because there is the presence of dependent variable that go along with this function. Okay. So take a look at here. This is x, so this must be expressed in terms of x. This is x, so this shall be expressed in terms of x. And again, if it is not linear, then it's non-linear differential equation. So a DE, yeah, a differential equation is not linear in the set of all of the dependent variables. So it's called nonlinear. Some of the examples are, yeah, let's see. The second derivative of x with respect to t plus k squared x equals 0. So remember that x is the dependent variable and that t is the independent variable. Okay. So we can say that this is an ordinary differential equation. Yeah, you're right. And order of 2, degree 1. Again, the dependent variable is x and the independent variable is t. So what is this? Is it a linear or nonlinear? Since this can be expressed of this form, okay, so therefore this is a linear differential equation. And one more. The partial derivative of w with respect to t is equal to a squared times the second partial derivative of w with respect to x. Characterizing this differential equation, we can say that there is a presence of partial derivative. So this is a partial differential equation of order, yes, that's of order 2 and of degree 1. Since this is raised to the first power, this is also raised to the first power. Okay, and then the dependent variable is w, and the independent variables are x and t. Again, the independent variable can be found, if you want to call it denominator, yeah. And what do you think? Is this linear or non-linear differential equation? Okay, so this is a linear differential equation, linear in t and linear in x. Another example, say you have the quantity x squared plus y squared dx plus 2xy dy equals 0. Okay, So again, earlier we have presented two ways on how to express this differential equation, one of which is the quantity x squared plus y squared dx dy by dividing each term by dy. Yeah. So you have dx dy plus 2xy equals 0, or dividing this by dx. Okay. So you have the quantity x squared plus y squared plus 2xy dy dx equals 0. So let us characterize this differential equation. So is this ordinary or partial? Since the given derivative is ordinary, then that's an ordinary differential equation. And it's of order 1 and degree 1. You can see it right here. So the highest order is first order derivative, and it's raised to the first power. So as on the equation 2, dy dx raised to the first power. And then what happened? What is the dependent and independent variable? For equation 1, you see that the dependent variable is x and the independent variable is y. For equation 2, you see that the dependent variable is y and the independent variable is x. Okay. And what is this? Linear or non-linear? So when you take a look on equation 1, so our independent variable is y, but when you distribute this dx dy, each term here, so you have x squared dx dy plus y squared dx dy plus 2xy equals 0. So what did you notice? There is a term containing dx dy that go along together with x squared, which wherein x is our dependent variable. So therefore, this is non-linear in y because of the presence of x squared dx dy. Okay. Next, what about the second equation? Can we say that it's linear in x? So when you try to see the second equation, so you have your x squared plus y squared plus 2xy dy dx. Again, our independent variable is x. So this equation or this expression should be written in terms of x. Remember this b sub 0, b sub 1 of x, b sub 2 of x, or b sub n of x. So this is our b sub n of x. However, there is the presence of y. That's why we can say that it's also nonlinear in x. So this differential equation is nonlinear in both y and x. Let's see if we still have another example. Another one. This time we have the quantity x plus y dx plus 3x squared minus 1 dy equals 0. Again, just like the previous example, we can rewrite this into two forms, one of which is x plus y plus 3x squared minus 1 dy dx equals 0, and the other one is x plus y dx dy plus 3x squared minus 1 equals 0. So we just classify this differential equation. We have an ordinary differential equation, you get it right, and of order 1, degree equal to 1, first order, first degree differential equation. On the first equation, we have the dependent variable, obviously is y, and on the second, and the independent variable is x. On the second equation, okay, so the dependent variable is x and the independent variable is y. Okay, and then let's classify it. Either is linear or non-linear. We say that equation 1 is linear in y because when you try to examine dy dx go along together with 3x squared minus 1, which is written in terms of x. There is no presence of y here. So this is our b sub n of x. Okay? So b sub n of x should all be written in x. And then y should not appear here. And therefore, since there's no y here, so it's linear in y. And then, in equation 2, it's nonlinear in x since there is the presence of dx dy times x plus y. Sorry, that's x plus y dx dy. So that's nonlinear in x since when you distribute this inside, so you have your x dx dy plus y dx dy. Again, this is y. So dx dy should go along together with an expression in terms of y. So this is our b sub n of y. So since the independent variable is y. However, on the first equation, the independent variable is y, but there is a function of x here. Okay, where x is our dependent variable. So that's why equation 2 is a nonlinear differential equation. We have some more. Yeah, okay. So we have 3t squared times the third derivative of y with respect to t minus sine t times the second derivative of y with respect to t minus cosine of ty equals 0. So we just classify this differential equation, number 1, by its type. It's an ordinary differential equation. Yeah, it's of order 3 because you can see the third derivative, you can see the second derivative, and yeah, the highest order derivative is equal to 3. Now, what about the degree? So we define degree as the highest power of the highest order, the highest power of the highest order derivative. However, you see here, we might say that the degree of this differential equation is equal to 1 since the highest order, the third derivative, is raised to the first power. But when we try to look at cosine ty, we shall consider that cosine ty, so this has no degree since the equation cannot be written as a polynomial in the unknown function y and its derivatives. Yeah, because of the presence of cosine ty. And still, the dependent variable is y and the independent variable is equal to t. And this is nonlinear, again, because of the presence of that cosine ty. Okay? And then let's manipulate this equation and what will happen. And I think this will be the last example for this presentation. So we have 3t squared times the third derivative of y with respect to t minus sine t times the second derivative of y with respect to t minus y times cosine of t equals 0. What did you notice? It's this cosine ty becomes y cosine t. Okay? So from here, so I write it of the form y cosine t. Again, this is an ordinary differential equation of order 3. Okay, since there's no presence of the dependent variable as a parameter of cosine, so we can now say that the degree of this differential equation is equal to 1. And the dependent variable is y, still y, and the independent variable is still t. So what is this? Is this now a linear or nonlinear differential equation? What do you think? Yeah, you get it right. It's a linear differential equation. Okay. And that's it for now. So you keep on tuning into my channel and I'll be presenting more videos on differential equation.